Okay, so let me finish up this container part by filling in some of the details that I missed out last time. So let's recall briefly what were we trying to do last time. We're trying to prove this theorem of Balog and Shoei-Moshe that alpha n is at most n to the 5/6 plus little 1. So what does that mean? Translated to a statement, that means we need to construct a set of endpoints on the plane such that it does not contain 4 points on the line, no collinear 4 points, but it's very rich in collinear triples, meaning that no matter how you take a subset of size slightly larger than n to the 5/6, you must necessarily contain in this subset a collinear triple. So the outline, the construction, is a mixture of structure and randomness. So let me highlight this. It's a mixture of some structure and then you do some random sampling. This is a thing that we will see later today on this Ramsey construction for K4 versus a clique. We start with something structural and then we do some random sampling. So here, the initial discrete object with the structure we want is we want something. Let's look at what we want. We want something that has no collinear 4 triple, but very rich in collinear. Sorry, we want something that has no collinear 4 tuple, but very rich in collinear triples. So the initial object we start with better has many collinear triples, right? So it's rich in collinear triples, but it has maybe not 0 collinear 4 tuples, but ideally very few collinear 4 tuples. So if we do random sampling, then because the order of decaying for collinear 4 tuples p to the 4, when you choose a point with probability 4p, and the order of decaying is p to the 3 for collinear triples, the collinear 4 tuples will die out much quickly. So the initial object we choose is very simple one. It's m to the cube, the discrete cube. And we've seen last time that the number of collinear triples is at least the lower bound m to the 6. Easy to prove. So the detail that we missed out is that we will actually have supersaturation for the collinear triples. So this is something we will prove today. And we get the upper bound on the collinear 4 tuples. It's not much bigger than m to the 6. In particular, we will prove m to the 6 times log m. Then at the second stage, after we have this good structure, we do random sampling to get the random subset R of this discrete cube with probability roughly 1/m. Roughly 1/m. Then we will see that the collinear 4 tuples, initially it's like m to the 6, right? M to the 6 times p to the 4, that's the expected number that survived, is /m². And the number of points that survive is also roughly m². We start with m³ points, multiply by 1/m, roughly m². By playing with this error term carefully, some correct polylog factor, we can make sure that the number of collinear 4 tuples is much less than the size of the random set. We can use first Woolman deletion to delete the point from each of one of these collinear 4 tuple. Then we will get a set with almost all the points there. Let's say half remained. This will be our set of m points, roughly of size quadratic in m. And the final part, we have to show that no matter how we choose a set of size m to the 5/3 plus some error term, we will see a collinear triple. This is the part we use container. Okay, here we use container. So now we need two things. To use container, we need to show supersaturation. It's supersaturation. This is something we will prove today. And we also need to prove this thing. that we missed out last time. So it's not so hard. Let's see this proof. Some basic geometric statement. So the first thing, let's upper bound the number of four tuples, collinear four tuples. So some preparation is the lemma 1. Let's try to prove that in M cube, this discrete cube, the number of collinear four tuples is at most some constant, let's say 50 m to the 6 log m. Okay. So it's not much bigger than m to the 6. How do we prove this? Well, let's first set up some parameters. So we want to count collinear four tuples. Let's first parameterize, group the lines through the cube by their direction. So this is M cube. There are some lines going through, right? The lines will have going through some points in this cube. For each line, let's give some definition. For a line, L intersecting integer letters in at least 2 points. Whenever it goes through at least 2 points, then we can define its direction by the difference of these 2 points. Okay. Then we let SL, which is a non-zero vector in dimension 3 with integer coefficient, because you have 2 points with integer coordinates, right? Be the shortest vector in this set L minus L. This just means all the points P minus P, where P is in L intersects Z3, okay? So take the shortest vector, that's the difference of 2 integer points on the line, that we call that the direction of L. This is called SL, the direction of L. Okay, here's a simple fact that you can check. If L intersect, let's give this a name. Let me write size of L to be the number of integer points, the grid points L contains within this discrete cube, M cube. All right, this is the notation, non-standard notation. And let's call this the size of L. Okay, size of L is number of grid points in M cube contained in L. Good. This fact is that if the size of L is at least k for some integer k, then if you look at its direction vector, SL, the direction of L, then its infinity norm, meaning its largest coordinates, is at most m over k. Okay, why is this true? This just, if a line contains more than k points, all right, Why is this true? Well, first of all, suppose not. If SL contains, if this direction contains a coordinate, contains a direction whose coordinate is larger than m over k, then that means you start with a starting point, you step less than k times, k steps, you will go out of the cube in this direction. So you cannot contain more than k points. Okay, this is simple. Next, so what that means is that, thus, and what this means is that among the grid points that L contains, it must contains a point in the grid with a coordinate at most m over k, or at least m minus m over k. This just means if a line intersects the cube in at least k points, then there must be a point that's very close to the boundary, either at the initial stage, less than m minus q, or at the final stage, close to less than m over k to the final height, which is m. If none of this is true, then you can make one more step. The line will have more intersection points. Yeah. So you must have a point that's close to the boundary, basically. This is also simple. Now, let's give some more definitions. For a non-zero direction, so this is a direction vector, we will call a capital LS to be all the lines with direction S, the set of all lines with direction S. Formally, it's all the L such that SL, its direction is S, and let's say this is now empty. You contain at least one grid point, otherwise you don't need to consider those. And let's further define KS to be the maximum size of a line with direction S. So this is the maximum size of a line with direction S. Okay, good. With this preparation, we can first try to prove this. So first of all, let's observe a corollary of this fact that we have above. If a line is heavy, intersecting the grid with at least k points, then it contains a point that's very close to boundary. There's a corollary. 1. The number of lines, LS, remember, is the set of all lines with direction S. So now let's fix a direction S. S is fixed. If you fix a direction, then the number of lines in this direction is at most. Well, let me write down some constants, then I'll explain. So how to see this? Well, we know that with the direction fixed, every such line with this direction, it can have size at most k of s, meaning that it must contain a point with coordinate at most m over k of s, right? Yep, you must have a point that's very close to the boundary. And this is the closed boundary in one coordinate. So among 3 coordinates, you choose 2, that's you do whatever. You choose their coordinate m squared with no restriction. Now, the coordinate that's very close to the boundary, you do m over k, because it's close to the boundary. So in total, you have m cubed over k of s, right? Now, next, is the number of directions with the maximum size are bigger than k. There are not so many of them. This is at most 2m over k cubed, or at least m minus 1 over k cubed. Maybe there's a floor. Okay. Roughly m over k cubed. The proof of this is simple. The first one, I've just mentioned it, because you need to, for every this fixed, all you need to do is to choose a 1 point. This is the number of ways to choose a point close to the boundary. For the second one, the lower bound, why is it true? I think I mentioned it sort of last time. If how to lower bound the number of directions where the lines going through this direction is heavy, at least k, you just, in the cube, you take a subcube of size roughly m over k cube. Here, you can pick any direction, s, as your direction. And here, because this s, the infinity norm is small, stepping out k times will remain in this inside this box. So every line going through this with direction s will have size at least k. Okay. For the lower bound, just consider lines in direction s, which is this cube through the, or here our origin of the cube is 0.111. Okay. For the upper bound, why is this true? This is just simply because if every point, every line is size is at least k, then its direction must have infinity norm less than m over k. So this choice of s is at most, for each one of these coordinate is less than m over k. So in together, m over k to the infinity. It's because okay. Now we can prove this upper bound. It's through basically a careful counting. Proof of lemma 1 that the number of collinear four tuples is at most m6 log m in m cube. The number of such collinear tuple equals to, let's look at the line intersect the cube. Look at its size. For every line, look at the size of it, meaning the number of points that the grid points it contains. you choose 4 of them. Every 4 points on the line, they form a collinear 4 tuple. Okay? And we have to sum over all lines. So we're going to group lines by their direction S. Okay, so this is how we group the lines by direction S. You fix the direction S, and you fix a line in direction S in the set L of S. Now on this line, you choose 4 points. That's exactly the number of collinear 4 tuples. So now we further characterize this intersection size by K. So this intersection size, let's say if this is K, then we sum over the intersection size has to go from at least 4 to m. A line can contain at most m points in this cube, right? Then, after you fix the intersection size, you choose those direction S where the maximum intersection size is K. K of S is the maximum intersection size with direction S. For every such line, S, the number of lines is exactly the cardinality of L of S. That's the cardinality of this. And for each one of this line is K choose 4. All right. Now we do a dyadic partitioning of K, meaning we partition K into intervals that are dyadic intervals. So this is at most. This here is actually at most because this Ks is the maximum. So this is at most sum over dyadic partitioning. I go from 1 to log base 2 of m. So now we're going to choose S where Ks is not K, but within 2 consecutive power of 2. This is dyadic partitioning, standard trick. So now this K to the 4 becomes what? We know K is at most 2 to the I plus 1. So K to the 4 is 2 to the I plus 1, choose 4. Okay. What's the size of, what's the number of lines with direction S? Well, we proved it above. The number of lines with direction S, when S is fixed, is m cubed over its corresponding maximum K. So we plug in here, this is 6m cubed over K of S minus 1. Okay. But what is K of S minus 1? It's 2i. K of S is 2 to the I, right? All right. Now, anything else? This is at most sum over all I. And then, now we have to choose, we have to count the number of directions where Ks is between 2 to the I. We have to count the directions where the number of, the size of S, this is here, the number of directions where the corresponding size is at least K, which is at most 2m over K. So this is at most 2m over K, but K is at least 2 to the I to the cube. This is this term. All right, multiplied by the remaining term. Now, if you do this calculation, this will be at most 50 m cubed log m. This will finish the proof. Yeah, just some counting. this is how we control the number of collinear four tuples. The very last missing ingredients for very last detail that we missed out is at the last stage, when we do random sampling, we need to prove that every set of size m to the 5/3 has a collinear triple. And here we need to use to prove a supersaturation to be able to invoke hypergraph container theorem iteratively. And we mentioned how we do this last time. So this time we just mentioned the supersaturation parts. So the supersaturation statement that we need is the following. Lemma, supersaturation for collinear triples. He says the following: for any subset of the grid M cube with size bigger than 100 M square, then the number of collinear triples in A is at least what? Some absolute constant times A cube over M6. So this is quite tight, because if you let A to be of everything, say, what's this bound? A cube will be, sorry, A to the 4. A to the 4 will be M to the 12 over M6. So you will get at least some M6 collinear triple. This is optimal. Actually, the number of collinear triples in the whole cube is roughly M to the 6. Okay. So this is the supersaturation. How we prove it? We do counting again, basically by convexity, Jensen's inequality. So let's let fx to be this x choose 3 convex function, but we need to make sure that x is at least 2. Otherwise, this is 0. It's not defined. So fx means what? When x is less than 2, it's 0. If it's at least 2, we define it to be this x choose 3 convex function. So this is convex. And the basic property is that fx is bigger than x cubed over 20, let's say, for any x at least 6. It's easy to verify. All right, so now we're going to use convexity. The number of collinear triples in A is at least, again, we grew up lines by their direction. You choose a direction. Now I choose a line in that direction. Then I look at how many points of A this line intersect with A, right. How many points L intersect A contains. For every triple of these points, they form a collinear triple in A. So that's exactly the number of triples in A. This should be equality probably. All right. Now this equals to, it's probably equality, I feel like. This equals to what? Oh, now we can use our function to write it, right? S, L in LS. This is basically f of it. We only care when the intersection is at least 2. Otherwise, this is 0. So this is f of the size of L intersect A. Okay. Now we can, because this is a convex function, Jensen's inequality, meaning that this inner summation is minimized when everything is averaged. Okay, so it's at least sum of S inside means everything is average. First, multiply the number of terms, and then f of the average. Average means what? You sum up over all these terms. Then divided by the number of terms. This is the average size of the intersection of L aligned with A in direction S. All right, this is just Jensen's inequality. Now, let's further simplify it. We know that this thing, fx, is at least x cubed over 20 when x is at least 6. So this is at least sum over all directions where the number of terms, so this number of terms is what? We have to look at here now. This is what? This is actually precisely size of A, probably. Right? Wait a second. L intersect A for all points. Right. If you fix, no matter how you fix the direction, so the key thing to notice is that this is numerator is size of A. So let me write one more line. This equals to sum of S LS times F of A divided by L of S. All right, why is this true? Anyone? No matter how you fix the direction S, let's say you fix the direction inside this box and you have A somewhere, right? I can always choose a line in this direction to go through every point in A. So if you're ranging over all lines in that direction, we can cover all the points in A. And every point is counted exactly once because the direction are all fixed. All right, so this is A. So we have this guy. And we know this fx is at least x cubed over 20 when x is at least 6. So we only need to consider those where this is at least 6 to lower bound it. So this is at least sum over all directions where this thing is at least 6 means the number of lines in direction S is at most A over 6. So this guy will be at least 6. You consider a subset L of S. Now I can replace this fx by x over 20, x cubed over 20. So it's A over LS cube over 20, 1 over 20. That's it. This equals to A cubed over 20 times the sum. 1 power cancel out. You have 1 over LS squared of the direction where number of lines in this direction is at most A over 6. 1 over LS squared. Okay. Now, final step, we're going to choose our K cleverly. So we're going to choose K to be some constant over A, so that, why we choose this K? So if the size of this direction, this is the largest intersection size of a line in direction S, is bigger than this chosen K, we get that the size of LS, the number of lines in direction S, is at most one of the previous things that we prove. If the size is K, then the number of lines in direction S is at most M cubed over K. This is what we observed earlier. By the choice of K, this is less than A over 6. So this sort of choice of direction satisfies this summation, the requirement here. Okay. Now, also recall the number of lines, the number of directions where the corresponding heaviest line with size K is at least M over K cubed. Remember, we can choose in the smaller subcube an arbitrary direction and step out K step. So this is the number of directions satisfy these. With our choice of K, this is bigger than, just use M over 2K cubed. Okay. So we are done, because now let's look at this term, the final term. Is at least A cubed over 20, the sum. So instead of summing over directions where the number of lines in this direction is less than A over 6, we can just sum over all directions where the largest size is bigger than K. This will imply the thing we want. So you just sum over all S where K of S is bigger than K. And such choice of direction, the corresponding 1 over LS is at least this thing squared, the reciprocal. So K over 6M cubed squared, which is at least, we know the number of summons, which is this guy. Okay. A cubed over 20, M over 2K cubed times K over 6M squared. Okay, this, if you do the calculation, is at least A to the 4 over M to the 6, some constants. Basically some calculation, a careful calculation to count. Any question? That will conclude what I want to talk about for container. And we're going to move on to the next part, which is constructions, various constructions in extremal combinatorics. And the next construction I will talk about at very high level has some similar flavor as this strategy. We start with some initial structure that's highly structured. it's quite good for what we want. Now we do some random sparsening to get the structure that we want. So it's a combination of structural and randomness. And oftentimes, in many cases, like here, or like in the next case, this Ramsey problem, we can do much better than pure structural construction or pure randomness construction. So a combination of two in the recent decade has found this sort of strategy has found many improved bounds, including some breakthroughs in extremal combinatorics and Ramsey theory. So the next constructions. So the first construction I will talk about is these so-called random block constructions. Random block constructions. Let's recall some of the basic backgrounds on Ramsey. The Ramsey RST is the minimal integer n such that for any two-edge coloring, of the complete graph on m vertices, we will get either a red copy of Ks or a blue copy of Kt. Okay. Today we're going to talk about off-diagonal Ramsey. So off-diagonal means S and T, they are not the same. Let's talk about off-diagonal, meaning S is fixed while T goes to infinity. Okay. In this case, the best bound we have, the upper and lower bound, is for fixed for any S at least 3. The Ramsey RST, again, this is fixed, and this goes to infinity, is at most some constant depending on S times T to the S minus 1 over some log factor. So let's say log T S minus 2. The lower bound, this upper bound is by I-type convolutions and similarity. And the lower bound, the best lower bound is by Bochman and Kivash by analyzing this random KS3 process. This is random KS3 process. By Bochman and Kivash, who proved the lower bound some other constant depending on S, T to the S plus 1. S plus 1 over 2 over some log factor, log T. Here the power of log doesn't really matter. All right. Forget about this lower order term. Just look at the polynomial. There is a gap when S is at least 4. When S is 3, everything is known. So when S equal to 3, this is the triangle Ramsey. Oops. 3t, which is order of magnitude t squared over log t. even the power of log is known in this case. So this is lower upper bound by Kim, and upper bound, what's the earliest upper bound nailing down? Maybe upper bound is the same. It's by I-type convolution similarity. Okay, so this t squared over log t. S equal to 3, this is 2. S equal to 3, this is 2. But when S equal to 4, the best known bound was R40 is at most 1 plus little o1 times t cubed over log t squared. But the lower bound by random constructions is only t to the 2.5. Over some log factor. Here, the log factor doesn't really matter that much. Okay. And today, the construction I want to sketch is a lower bound, a recent breakthrough matching this upper bound. Matching this t cubed power. So, theorem by Matthews and Verstraete is 2024, I think, very recent. In their breakthrough, they prove almost matching lower bound R for t is at least some constant t cubed over log t to the power 4. So there is still a lower order term, log-wise. They conjecture, they believe it should be log square, I think. So there's a conjecture. Improving this log term, it will be very interesting. So far it stands between 2 and 4. If you can get anything that's smaller than 4, it will be interesting. The conjecture is R for t, the upper bound is correct. T cubed over log t squared. Okay. So how do we let me first sketch a proof of the idea. Any other comments I want to make? Any questions? Okay. And then they also prove a multicolor version. Earlier, along with Rödel, who answered a question of Erdős that what's the notation? RK3T. This is notation. This means what? It means you have K colors forbidding triangle, and the last color forbidding a KT. It's a multicolor Ramsey. They prove that this, up to the polylog factor, they can nail down the a polynomial of this Ramsey number. It's t to the, let's see, when k equal to 1, it should be t squared. So it's k plus 1, I believe. K plus 1. So it grows by, you're adding one more color of forbidden triangle, you grow by a factor of t. So here, using similar ideas of the construction there and their construction for R4T as black box, they can obtain also multicolor, a tight multicolor for R4T. So here, this is again, Matthews and Verstraete. They prove RK4T is up to the big polylog factor. This is their lower bound. Upper bound is by He and Wiggerson. So here it's big theta of t to the 2k minus 1, I think. Yes. So when k equal to 1 is t cubed. And whenever you add the color, you grow by a t squared. Yes. So coming back here, let's try to prove this. Forget about multicolor for now. How do we prove a lower bound of t cubed up to polylog for R4T? So what we want is what? Let's write down what we want on the side. If this is n, we need an n vertex graph G, which satisfy that it's K4 free. Okay. Wait 1 second. So what do we need to prove? We want to prove the lower bound on off-diagonal Ramsey number R4T is at least up to some polylog factor t cubed. What it means is that we need to construct, the, so let n to be roughly t cubed. We need to construct the n vertex graph G, which is K4 free, and its independence number is at most t, which is roughly n to the 1/3. Okay, this is what we need to do. A lower bound construction for Ramsey. It's K4 free, and it does not have large independent sets. The largest independent set is roughly n to the 1/3, where n is the number of vertices. Any questions about this statement? I'm just translating the definition of lower bounding the Ramsey number. Okay. So how do we do that? It's again a combination of structural and randomness, and the structure coming from some finite geometric objects. I will not dive too much into the finite geometric objects. I will only state their combinatorial properties, and then we will see how we can use these combinatorial properties and use randomness to make it, to massage it into this graph that we want. M vertex graph, K4 free, independence number is at most n to the 1/3 roughly. Okay. So here's the strategy idea. The idea, the finite geometric part only comes in the first step. The construction coming 3 steps. In the first step, we construct a graph from finite geometry. We call it HQ. The graph HQ from finite using finite geometry. Now let's list what the properties This graph HQ has n vertices. N is roughly q to the 4. Whenever I write this tilde, I just means up to some polylog factor, okay? So roughly q to the 4 vertices, this graph. And this graph is roughly q cube, regular. Every vertex has roughly q cube degree. And the next two properties are very important. Its edge set, the edge set of HQ, it looks something like this. The edge set of it is a union of maximal cliques, and the cliques, they pairwise intersect at most one vertex. Is a union of roughly q cube, meaning maximal clique, each of size roughly q square. Okay, and these cliques pairwise sharing at most one vertex. So they are kind of tangent to each other, you see? So the edge set of HQ is very structured. You can decompose the edge set into maximal cliques. Each clique is of size q square. Each one of these is like kq square. And the number of cliques is q cube. Number of cliques, roughly q cube. And they pairwise intersect no more than 2 points. No more than 1 point. Okay, so this picture is not so good. So they pairwise share at most one vertex. This is their property. Finally, the very last property, very important one, whenever you have a K4, for every K4 in HQ, you definitely can find a triangle, at least 3 vertices in this K4 that lies in one of these cliques. Then at least 3 vertices in this K4 lying in some of this maximal clique. Okay, so if you have a K4, at least one of the, let's say you have this K4, you can find 3 vertices. These 3 vertices lies in one of these. Okay, it's impossible to have 2 vertices in one maximal clique and 2 from the other. This is impossible. You cannot have a K4 that look like this. That's what it means. All right. So far, so good. Okay. So why this is the initial very structural part. Why? Let me explain intuitively. This is sort of good for us. It puts a lot of restriction on, well, first of all, the edge set of this graph is already highly structured. It can be grouped into cliques. And pairwise, the clique, they are not much intersect at most one vertex. This is one highly structural part. Second of all, it puts lots of restriction on K4. Okay? So we need to massage into what? The first property is we need to make sure it's K4 free. Second property, there's no large independent set. So how do we kill all the K4? Well, look at the last property. We know that every K4 must have a triangle contained inside a clique. So if we replace every one of these maximal clique by some triangle-free graph, we kill all the K4. Does it make sense? So how we replace this? This is the second step. We replace it not just to triangle-free graph, we even just replace to bipartite graph, which definitely is triangle-free. So and how we replace it is very simple. For every one of these cliques, we know the edge set can be partitioned into these cliques, right? For every one of these cliques, we just replace it by a random bipartite graph, complete bipartite graph, where each part is formed with probability 1/2. So with probability 1/2, you cut this clique into 2/2, and you only keep the cross edges. So now each clique becomes a complete bipartite graph, in particular triangle free. And we know that every K4 must have a triangle inside some clique. We kill all the K4. So this is the second step. Let me write it down. This is the random block construction. We will get HQ star. How do we do it? Let me give this name. Let's call this clique C1, C2, CI. Okay, roughly Q of them. So for every clique, CI, we replace it with a random complete bipartite graph. What it means is that this is CI, okay? Then I randomly, with probability 1/2, throw a vertex here, with probability 1/2, throw the vertex to the right. Then we only keep all the edges going across, okay? And by concentration of measure, most of the time, this clique roughly has half of vertices on each side. This is easy to prove. Now, because of this loss property, this nice property that every K4 has a triangle inside some clique, by doing this, HQ star now is K4 free. So because of this property, we know that HQ star is K4 free. We obtain the first property, all right? Now we need to do random sparsing to make sure that there's no large independent sets, the second step. All right. And to do that, we also use Lyman-Winston's container. It's used here. So to do that, to use container, we need to prove local denseness. This is some sort of pseudo-randomness property. Let me state it here. First of all, I want to say that this step is well defined. Which property we use to make sure that this is well defined? Every clique share at most one vertex. So every edge is containing, because of this, every edge is containing exactly one clique. There's no confusion when we do this partitioning one by one. All right. If there's some clique, they intersect at more than 1 point, this partitioning doing one by one, they are not independent events, right? Here, because they share at most one vertex, every one of these CI, random by partition, it's independent event. Okay. Let me just state as a remark here. Now, good. So let's see. But this graph, I want to mention that how large of the independent set this graph can be. This independent set probably could be quite large. So number of vertices of H cube is still Q to the 4, right? But now the independent set is of size Q squared, right? Every this clique, we replace it by complete bipartite graph. And remember, this clique is of size q squared. So this complete bipartite, we have a huge hole here, q squared. All right. But let me write here. But alpha of HQ star is at least q squared up to some polylog or constant factor, q squared. This is not quite what we want because the number of vertices is q to the 4. What do we want? If this is n, we want n to the 1/3 for the independence number. So we need something to below q to the 4/3. This is like root n. It's too big. And here's how we do random sparsening, the random sampling to Q. We want to show that there are not so many independent sets much larger than Q log some log power. Set T to be this guy, okay? The number of independent sets larger than this threshold, there are not too many of them. Now, by randomly sample a subset of vertices and look at the induced subgraph, this size T independent set, because there's not so many of them, first moment deletion, you can kill all of them. Of course, by taking subgraph, you remain the K4 freeness, and the number of vertices drop a little bit, but the independent set drop more. That's the last step, step 3. We do random sampling. We sample every vertex with probability P up to some polylog factor. Let me not worry about polylog factor, roughly 1/Q, okay? To get the final graph. Let's call it G. So G is a subgraph of HQ star, yeah? So let's see, now the parameters will check out. Well, first of all, what we need to do here is, okay. So here, what we need to show is the number of vertices, first of all, is easy to check. Initially, we have Q to the 4 roughly vertices. We sample things with probably 1/Q, so G has roughly Q cubed number of vertices. Okay. What about independent set? This is something we need to prove. Listed in blue, there's no independent sets. Of size T, which is roughly Q. Some Q log Q power, okay? If you want to see the log Q power, let me check. This is Q log Q squared. Some constant. Q log Q squared. Okay, so this is roughly what? Now this is our n. This is roughly n to the 1/3 up to log factor. And we are done if we can do this. If we can do the last line. Okay, once again, the construction has 3 steps. Let's review these 3 steps. First, using some finite geometry objects, we get the initial graph HQ, which is the structured object. It has Q to the 4 vertices. Every vertex has degree Q to the cube. Yeah. And the structural part is that its edge set consists of union of these tangent cliques, pairwise sharing at most 1 vertex. The number of cliques is Q cube. Each clique is of size Q squared. Okay. Another important property is that every K4, if you ever have a K4 in this graph HQ, then at least 3 vertices of this K4 must lie in one same clique, one of these CI. So our first step, which is the second step here, random block construction, is to kill the K4 to get our first property. How do we kill the K4? By the last property, every K4 has a triangle inside some clique. So we make sure that every clique replace it by a bipartite graph. no triangle, then K4 will get annihilated, get killed. So we replace every clique Ci here by a random complete bipartite graph. You just throw vertices on each side with probably 1/2, put edges in between. Good. So let's call this graph HQ star. This is the random block construction. So HQ star is K4 free. We have the first property. But the independence number is not small enough. We want independence number to be roughly n to the 1/3, remember? To get the Ramsey number Q cube for R4T up to polylog factor. But here, independence number obviously is at least Q squared in this random bipartite graph. And number of vertices is Q4. This is root n. We're going to do a random sampling with probability P, roughly 1/Q, to drop the vertices down to Q cube. And we will prove that there's no independent set of size roughly Q, which is n to the 1/3. So how do we achieve the last part? Here is we need the local randomness. To achieve we need the graph HQ square to have some sort of pseudo randomness, to be some pseudo randomness. In particular, locally denseness. This is a lemma. That in HQ, where everything is with high probability, because HQ star is replaced by random bipartite graph. So this is a random event. So this random graph with high probability will be locally dense in the sense that for any set X of size, some 100 Q square, 100 doesn't matter, some constant times Q square number of vertices, then it's dense. The number of edges there induced on X is at least some constant X squared. Okay. Here, well, first of all, let me explain these parameters here a little bit. The first explain is why this density? Why H density 1/Q? This is the best we can hope for. Why? Well, not to mention HQ star. If you just look at HQ star is a, okay, sort of. HQ and HQ star, the only difference is we replace the clique by complete bipartite graph, right? So the edge density, there's no change up to a factor of 2. All the edges there are complete bipartite graph up to a constant factor. So their edge density is same order of magnitude. So let's just look at HQ. In HQ, the number of vertices is Q to the 4. Degree is Q cube. So the edge density is Q cube over Q4, which is 1/Q. So if you uniform random pick 2 vertices in this graph, HQ or HQ star, the probability that you see an edge is 1/Q. So this 1/Q is the correct edge density for the pairs in X, right? This is the number of pairs in X, and Q is the edge density. So this is edge density of HQ or HQ star. So this is best possible. And also here is also best possible, at least Q squared. Because it's also because HQ star contains an independent set of size Q squared, right? So if you are small constant times Q squared, you could have 0 edges. This is also best possible. Okay, this explains these parameters. The proof of this, let me first tell you intuitively why this is true. I will not prove it, definitely not today. The proof is not hard, just by some concentration inequality. The proof is by concentration inequalities. Let me first convince you why this is correct, why this is believable. Let's prove it like a pseudo proof. Let's try to prove it in proof for HQ, not HQ star. If you don't do this random bipartition, it's easy to prove. And doing this random bipartition intuitively, it doesn't affect local densities, right? The edges are still there, at least, when the set is much bigger than Q squared. But this pseudo proof that we carry out, it will fail for this HQ star. It works for HQ. This is a spectrum proof. Let's try to use a spectrum proof. So how do we prove it? It's not hard. It's known that for this graph HQ, what's the first eigenvalue? The first eigenvalue, because it's a regular graph, the first eigenvalue is its degree, roughly Q cubed. And it's known that the second eigenvalue equals to, let me write it down, Q squared minus Q minus 2, where the multiplicity is roughly Q cubed. And the last eigenvalue is minus Q plus 1 with multiplicity roughly Q to the 4. Roughly Q to the 4. Okay. Now, how do we get a spectrum proof? You use the one-sided expander mixing lemma. So by one-sided expander mixing, for example, along chain, you can show that the number of edges induced on the set is at least the edge density. Edge density means D over N, right? Edge density times X squared. Minus plus the smallest eigenvalue times something like this. I think this is the one-sided expander mixing. Now, if we take X to be, so this term, you can think of this term can cancel out up to constant. Yeah. So we want this to be error term. This is the expectation. Okay. And what do we have? You have EX is at least D over N. B is Q to the 3, N is Q to the 4. So this is 1 over Q X squared up to some constant. Yeah. Minus lambda N is Q. So it's Q times X. You want this to be error. That means this main leading term must be larger than the error term, right? This implies X must be at least Q squared. Yeah. So when X is large enough, this guy becomes an error term. And you have this the leading term, which is 1 over Q density times this. That's what we need here. And why it fails for HQ star? It fails for HQ star because we replace the clique CI by complete bipartite graph. Each side is Q squared. In particular, this KQ square graph has eigenvalue, minimum eigenvalue negative Q squared bipartite graph, right? By Cauchy interlacing, we know that HQ star, the minimum eigenvalue is also negative Q star square, not negative Q anymore. And that this negative Q square will result in the square here, requiring X to be at least Q cubed. You will get a much weaker local denseness. You require the set to be much larger. Okay, let me write it here. For HQ star, this one will not work. This is not ideal, as KQ square is a subgraph of HQ star, and the minimum eigenvalue, let me write in the second page, and the mean eigenvalue of KQ square obviously is negative KQ square, negative Q square, and Cauchy interlacing just means the eigenvalues of induced subgraph of a graph and the original graph, they are interlaced together. So interlacing implies that lambda n of HQ star is less than negative Q square up to some constant. So this will require to have error term be truly error term. We need X to be at least Q cubed, which is not good enough. So we need to use some concentration inequality. Okay. In the last 5 minutes, probably we will prove this next time, or I might even just skip this proof. It's using martingale bounded difference inequality. This is not hard to prove. So let's assume this for now, and let me convince you how we can use this local denseness to prove that if you do this sampling, the independence number will drop from Q squared in HQ star down to roughly Q in this subgraph G. That's the only thing we have to convince ourselves, right? So this is the very last step where we use this container theorem. So we will use container theorem to achieve star. To obtain that, what this means is alpha of G is less than T, right? This T is some constant times Q times log Q squared. We need to bound the number of independent sets of size T. Let me call it IT. IT is good. In HQ star. The number of independent set of size T in HQ star. And we want to bound it so that this number, let's call it M. Then when we do for each one of these, each size T independent set, the probability It survived. Let's call it I. I is in G is what? Is precisely P to the T, right? It's of size T. Each vertex is retained with probability P. It's P to the T. So we want what? We want M times P to the T to be less than 1. That means in expectation, after the random sampling, when you pass from HQ star to G, this random P sampling, this guy is the expected number of size T independent sets. In G. And if this expectation is less than 1, that means there exists choice of G, exists the choice of sampling, such that the number of size T independent set is strictly less than 1. But this must be an integer. Strictly less than 1 means 0. There's no independent set of size T. Oh, that's exactly what we need. Alpha of G is strictly less than T. So all we need to, there's nothing to do here. P to the T is P to the T. We know what T is. So the only thing to do is to bound M, the size of the number of independent set of size T. But now it looks familiar, right? Remember Kleiman and Winston that we proved. In HQ star, in this graph, if you want to bound the independent set of certain size, and you have locally denseness, you just plug into the Kleiman-Winston, you can bound it. All right, we will do that next time. So, and this is achieved to bound M. We use local denseness of HQ star and Kleiman-Winston container theorem. That's the final stage. This is the proof without calculation, basically. So when you see up to this point, we should be able to carry out the proof ourselves. But next time I will show the details. Any question about this idea of the construction? Okay, let me say one more time. We start with some initial highly structured thing with some nice property that's quite close to the property we want. Not K4 free, but it has a lot of restriction of K4. Remember last time for this Erdős 4-3 problem is the same. Not that the M cube has no collinear 4 tuple, but it has very few collinear 4 tuple. So hopefully later when we do random sparsing, we're going to kill all of them. So in this case, all K4 has a triangle lying in some clique. So replace clique by this random block. This is where the name comes from. Random by 2 block, complete bipartite graph. You're going to kill all the triangles inside each clique, thereby killing all the K4s in our original graph. We achieve one property. To get a second property, well, because the original graph has nice spectrum property, sort of pseudo-random, locally dense, we expect this random block version of original graph is still locally dense, which is true. It can be proved. And the locally denseness by Kleiman-Winston container method, it tells us that locally dense graph, you can bound its independent set efficiently. It doesn't have too many large independent sets. If it does not have too many large, by large I mean size T, independent sets, let's call this number M, then you sample vertices with probability P. Each independent set of size T retained with probability P to the T. We just need this expectation, M times this probability, to be less than 1 to achieve a graph with small independence number. Okay? So this first part, yeah, I will mention next time. I didn't say the details here. I only list the properties we need. So next time I will mention how we can go from, in particular, this is to use this so-called unital structure inside the projected plane. It has some nice property to achieve all these things. So next time we're gonna see some details of this. Okay.
HQ 新的独立数的话，如果我们从每个 click 里拿一个点的话，它这个独立数就是 Q 的3什么？
Let me think. The independence number of HQ star. So these maximal clicks, they are sort of intertwined together. If you pick one from each, it doesn't mean that you can pick so that there's no edge at all. They sort of complicatedly sit together. All we know is that the pairwise share at most one vertex. Okay.
在左边的话，我们取一个 P4出来，它会不会就是比如一个部分取一个，另外一个部分取一个，然后它就会偏就是先这样的话，三角形就不再有。
我没听懂。
那如果两个部分之间有边的话，你就从上面一个部分到那个，然后中间填两个，然后就形成一个线。那这样的话，我在 HQ 里面取一个 P4的话，是不是得不到那个大于等于3个点在一个部分？
我回头再回答你问题吧。So any other question? Okay, if not, let's see. We're gonna continue on Thursday.